the primary source of an MR signal is the hydrogen nuclei. As I mentioned, hydrogen is present in water, and that's what the MRI machine kind of relies on. And so hydrogen nuclei consists of a single proton, and that's why it's referred to as just a proton sometimes. And that proton is constantly spinning. And because it's spinning, it's a moving charge, which means that it's an electrical current. And an electrical current generates a magnetic field. So protons can be looked at as little bar magnets. And what happens is that that means that they have a south and north pole. And they have this arrow that I have showed here, which is also called the magnetic dipole moment. And this arrow, the magnetic dipole moment, points from south to north, and magnetic field lines point from north to south. But this dipole moment is going to become quite important when we talk about how MRI actually works. So when an external magnetic field is applied, the protons, or the magnetic dipole moment, aligns with the direction of the magnetic field. So in a normal state, the protons in the body are randomly oriented. The magnetic dipole moment is facing in random directions. But when an external magnetic field is applied, they tend to align with that magnetic field parallel because they want to be in their lowest potential state. Most things in nature want to be in their lowest potential state, but it's not perfect because a few, and very few in comparison to the ones that align parallel, do align anti-parallel as well. But what's actually happening is that these protons that affected the magnetic field on the group of protons cause them to spin in a specific way, and this spin is called precession. And what happens is you have a bunch of protons that are spinning across this axis, and they're going to be spinning out of phase when that magnetic field is applied. And so when they're out of phase, you're going to have a proton at each point with one at an opposite point, and that's going to cause the vectors in the x and y plane to be canceled out. But the vectors in the positive z direction will add up, and this creates a sum magnetization, which is responsible for this vector over here, the longitudinal magnetization vector. Now, as I mentioned before, some protons are going to align anti-parallel, so they're actually going to be in the opposite direction, and their vectors are going to point in the negative z direction. So they are going to cancel out a few of the protons, but the ratio is very insignificant because there's a lot more of the parallel aligned protons than there are anti-parallel. So you're going to get a sum magnetization vector that is in that positive z direction, and that is what's going to be parallel to the magnetic field, basically what's happening here. And what happens is the MRI machine will apply a radio frequency pulse. And when these pulses are applied by the machine, that disturbs the protons. They tend to misalign. And so upon RF activation, two things happen. One is that RF pulse will transfer energy to the protons, and this is going to cause the protons to become excited, and they will want to move to their higher energy level. So as I talked before, generally the protons want to align parallel to the magnetic field because they want to be at their lowest potential. But what can happen is that once they get excited, they will move to that higher energy level and they will start aligning anti-parallel. And so as we saw in this figure over here, as more and more become anti-parallel, there's more vectors in the negative z direction, and this starts to reduce this longitudinal magnetization vector. And the second thing that happens is that the protons that were moving out of phase, but upon RF activation, they start to move in phase. And that means that they start to move in the same direction at the same time. So if you look at this figure here, if I had these two protons, they'll actually be like right on top of each other almost, and they'll be moving in the same direction at the same time. And that means that their x and y vectors can no longer be canceled out because they're facing in the same direction. And this creates a sum magnetization vector in the x and y plane, and that's called transverse magnetization. And what happens when you turn this pulse off is relaxation occurs. And from the previous slide, when we talked about those two directions, the type of relaxation that occurs depends on those two different things that happen. So first is T1 relaxation, which is also known as longitudinal relaxation. And this is that when the protons that were excited by those radio frequency pulses, when that radio frequency is turned off, they want to return back to their low energy state. And as they return back to their low energy state, more and more protons are now parallel aligned. And as they are parallel aligned, what happens when we initially talked about the external magnetic field is that longitudinal magnetization vector is restored. And T2 relaxation, also known as transverse relaxation, is that the protons that were in phase will start to precess out of phase when they no longer have that RF frequency. And what happens is those X and Y vectors that I talked about start to cancel out again, and that transverse magnetization recedes. So T1 and T2 relaxation occur simultaneously, and so you can basically look at it as a net magnetic vector, which is the sum of the longitudinal and transverse magnetization. And as transverse magnetization goes back and longitudinal magnetization starts to increase, this net magnetic vector basically precesses, it spirals as the same way a proton would. And it starts down here and it moves slowly upwards until it meets the z-axis. And what happens is that this changing magnetic moment produces a free induction decay, which is the electrical signal that will be picked up by the RF coils. And this signal, it is received when it is in the transverse plane. It's actually the strongest when it's transverse. So when this starts out, the signal is the strongest and it slowly makes its way back up to the aligned with the z-axis. It's weak. It gets weaker and weaker. And this FID signal is received by the MRI RF coils, and the computer system receives a signal from where it is converted through a series of processes to an image. And so that was kind of an overview of how MRI works on kind of a molecular scale. An atomic scale. And just going back to that T1 relaxation time. When an image is produced and there is a variation in the tissues, because each tissue in the body has different varying T1 relaxation times, an image that is produced where the differences in tissues is caused by that T1 relaxation time, it is known as a T1 weighted image. And T1 weighted images are useful when it comes to measurements such as cortical thickness. So over here, this is a T1 weighted image, and they've shown and indicated what cortical thickness is, which I will talk about a little bit later. But I wanted to bring some attention to this interesting figure where they compare kind of how these different scans look. And just focusing on T1 versus T2, you can see that the different tissues and different parts of the scan that show up are actually different in the two different types of images. So for instance, white matter in a T1 weighted image is light, while white matter in a T2 weighted image is darker. And it's a little bit counterintuitive for a T2 weighted image, but these two images are used for different measurements. And so I will talk about mainly T1 weighted images because we want to look at cortical thickness.